So for a linear growth problem, we have George, who's saving up for a bike that costs $150. He already has 42, and he started a lawn mowing business to earn the rest. And so altogether, he gets $12 a week from his business. So starting with the table, the start is 42, so at week 0, you have 42. And then you're adding 12 each week, so with each week, you're going to make the number 12 bigger, so I'm just adding 12. So for the graph, the y-intercept is 42, which is basically the start value. And then with each week, you're increasing 12, so the point will be 12 higher, but one x value bigger, I guess. For the recursive rule, the start is 42, which is the y-intercept and also the start, or like the start value for the week 0. And then each time, or like each week, you're adding 12, so it would be now plus 12 would equal your next, but then you're starting at 42. For the explicit rule, the y would be the output, which is the amount of money he has. The x is the input, which is the week number, and then 42 is where he starts, the amount of money he has when he starts, and 12 is the amount he increases each week, which is from where he gets his lawn mowing business and the money he makes from that. Lastly, for our predictions, for how much money he'll have after 10 weeks, we plugged it into the explicit rule, and we got $162, and then for the how many weeks it'll take to reach 300, you had to do it kind of backwards and solve it like a equation, like putting in 300 for the y, 22 for the x. Well, no, not for the x. 22 is the answer, so like you find that.
So this is exponential growth, and the predator becomes extinct in 2010, and the lizard's population increases by 30%. So this table goes out to 2015, and it increases exponentially because of exponential. So the recursive rule is next equals now times 1.3, and our start is 10,486, and our explicit rule is y equals 10,486 times 1.3 to the power of x. So this is a graph, and the x is labeled years after 2010, and the y is labeled the population of the lizards, and these are in the thousands, and it starts at 10,486 right there, and it goes over 50,000 in 2015. And so these are our two problems where we have to estimate using the equation. And so what will the population be in 2017? Round to the nearest whole number. Because it's a lizard, you can't have half a lizard. So in 2017, there will be 65,798 lizards. And when will the population be 111,200? That will be in 2019.
For the linear decay problem, we have Toby, and she has a jar of 100 cookies on her counter. And her mom, dad, and brother, they all eat 3 cookies each day, and then Toby eats 1 each day. So how many days would it take for all the cookies to be gone? For the table, the start is 100. For the x, we start at 0. And then the y is 100, and then each day you're subtracting 10, so the y is going down 10, and the x is going up 1. For the explicit rule, we have y, which is the output, which is the number of cookies there will be, and then 100 is the start, which is the number of cookies when they bought the jar, and negative 10 is how much they eat altogether each day, and x is the day number. For the recursive rule, it's next equals now minus 10, and the start is 100. So 100 is the number of cookies that they have when they first start. Next is the number of cookies that they'll have after that day. And now is the number of cookies that they have currently. And then negative 10 is the amount that they're eating each day. For the graph, we have the y-axis, which is the number of cookies that they have, and the x-axis is the negative number. So on day 0, they have 100, and each day they're going down by 10. So by day 5, they're down to 50 cookies because they've eaten 50 cookies. For the prediction problems, we started with how many cookies will they have after 7 days. So I plugged it into the explicit rule, which is y equals 10x plus 100, and I did 100 minus 10 times 7, since there's 7 days, and that's 30, so it would be 30 cookies. And then for how many days it would take to run out of cookies, we did the explicit rule again, and 0 would be the output since there's no cookies left. And then you do 100 minus 10 times x, and that would be 10.
So this is another exponential problem. The population of the African blue-spotted lizard is slowly decreasing due to its predator eating 20% each year. In 2003, the population of the lizard was 50,000. So we created a table that goes out to 2008, and as you can see, the population decreases, and this is a decay problem because it decreases, and the recursive rule is next equals now times 0.8, and the start is 50,000, and the explicit rule is 50,000 times 0.8 to the power of x. So on the x-axis, this is the years after 2003, and on the y-axis is population in thousands, and we can see that it starts at 50,000, and it goes down to about 15,000 in 5 years. So we used, this is an estimated problem. So what would the population be in 2010? Round to the nearest whole number because we're talking about lizards, and it would be 10,486 lizards. And when will the population be in 2200? That will be 14 years after 2003, which is 2027.